Starting out over here at Stellarium, where you always want to start. The sun is setting. We got Jupiter, Mercury over there. Venus, the lion's going to eat Venus. Virgo up in above us. And the moon. The moon's over here. What's that? Oh, a periodic comet. Maybe you see that tonight. Maybe. There's the moon. Zippity doo dah. Zoom out. Center. Boy, there's big giant mosquitoes out here, guys. And we'll go to right about there. Should be somewhere about 2:30 in the morning. Should be right. I think. Yeah. So about that time, center Jupiter, because it's probably the Jupiter or the Sun. So it's going to be, yeah, I would say about right around 2:30. So, boy, a bunch of bugs out here. Boy, big ones. Between 1:30 and 2:40, but 1:30 and 3 o'clock in the morning, pretty much is when we're going to see. If one pops off, it's going to be then or shortly after, guaranteed. Okay, so mapping Earth's hidden signals. I posted the other moon stations in post the other day ago that I went through, screenshotted. Big deal. Into the world, right? Whatever. Um, Copilot. Yes, I'm not Copilot. Some nice images there. Huh? I've done a lot since I've gotten out, huh? Oops. Go back. See? There's mapping myth and entropy now on my other channel. And now I privatized the live stream of that one and downloaded it, downloaded it on my other channel, the one I was on with all the AI stuff. So this is a video and some other videos that haven't been properly turned into videos. I'm sure I'm getting ate up out here. Look at I'm a proud boy. Look, proud boy. So 9 people watching. Okay, you ready for this? I haven't heard this one. I just put this one out. This took a long time to do today because I'm still waiting for the full pipeline to finish processing all this stuff. Uh, well, it's in another run, but it took like 2 hours for process all the what was going on. I hope this is a good one.
Welcome to Copilot Podcasts. Every single day, SARSAR satellites orbiting Earth generate over 5 terabytes of raw data. 5 terabytes every day. And buried inside that flood of radar pulses is the ability to detect ground movement down to the width of a few millimeters, map earthquake damage before rescue teams even land, and track tens of thousands of landslides across the globe. Today, we're pulling back the curtain on SAR and INSAR coherence mapping and seismic entropy overlay generation. Specifically, how the operational workflows actually run, what the cloud-native revolution means for who can do this work, and why the convergence of radar science and entropy-based seismic analysis is changing disaster response. By the end of this episode, you'll understand the full processing chain from raw radar signal to actionable ground disruption map. I've got someone here who lives and breathes this stuff, so let's get into it. Walk me through what we're actually talking about when we say SAR and INSAR coherence.
So SAR stands for Synthetic Aperture Radar. The key thing about it, and this is what makes it genuinely different from optical satellites, is that it sees through clouds and it works day and night. It's an active sensor, meaning it sends out its own radar pulses and listens for what bounces back. Now, INSAR takes that a step further. Interferometric SAR compares 2 radar images of the same area taken at different times, and by looking at the phase difference between those 2 signals, you can detect incredibly subtle changes in the Earth's surface.
And coherence is where it gets interesting, right?
Exactly.
Coherence is essentially a measure of how similar those two radar returns are. If the surface hasn't changed much between the two acquisitions, the signals are highly coherent, they match well. If something has disrupted the surface, an earthquake, a landslide, new construction, coherence drops. So a coherence map is literally a visual record of where the Earth's surface has changed and where it hasn't. That's a really clean way to think about it. So low coherence equals something happened there.
That's the core intuition, yeah.
And NASA's SAR handbook, which was put together as a collaboration between the Server program and Silvacarbon, describes SAR as a hands-on tool for forest change detection, biomass estimation, mangrove monitoring. But the same underlying physics applies whether you're watching a forest or watching a fault line. So the science is the same. The application just shifts depending on what you're looking at.
Precisely. And what's wild is that the Fringe 2023 presentation from the team at Descartes Labs, Piyush Agram and colleagues, showed that SAR and INSAR analytics now run inside the same GIS framework as optical data like Sentinel-2 or Landsat. The same band math operations you'd use to compute an NDVI vegetation index can be used to derive coherence and backscatter. That's a huge deal for accessibility.
Wait, so the same math that tells you how green a forest is can also tell you how much a hillside moved?
That's exactly right. The Descartes Labs team demonstrated this with Sentinel-1 data. They're producing global coherence products at 20-meter resolution with a temporal baseline of up to 24 days, and it's all derived on the fly using the same filtering and bandmath framework. It's a standardization that the SAR community has been pushing toward for years.
Okay, so now I want to get to the seismic entropy side of this, because that's where things get a little more abstract for me. What does entropy even mean in a seismic context? So entropy in this context is about uncertainty and complexity in the distribution of seismic energy. Think of it this way. After an earthquake, you have seismic stations recording ground motion at specific points, but you need to understand what...
Pardon the cicadas, they just came out today, and they're orange like, they're strange looking. But they'll be going for a while. I'm gonna try and cover the mic. Let's continue.
Happened everywhere, not just where the sensors are. Entropy-based methods help you interpolate that information in recording ground motion at specific points, but you need to understand what happened everywhere, not just where the sensors are. Entropy-based methods help you interpolate that information in a statistically rigorous way.
And there's actual research backing this up?
Very much so. A paper published in Frontiers in Earth Science in May 2024 by researchers at the Lanzhou Institute of Seismology, China Earthquake Administration, used what's called Bayesian maximum entropy, BME, to predict seismic intensity by combining station data with ground motion prediction equations. And the results were striking.
How so? They tested it against earthquakes in Japan, the United States, and Turkey. The BME method consistently outperformed standard spatial interpolation approaches like IDW and Kriging. It was more consistent with ShakeMap results, which is the gold standard for rapid seismic intensity mapping, and it corrected errors that simpler methods made, like predicting the wrong rupture direction for a US earthquake. It also handled situations where you have very few sensor stations, which is a real-world constraint in a lot of regions.
So the entropy overlay is essentially a probabilistic map of where seismic energy went.
That's a good way to put it. And when you layer that over an INSAR coherence map, which is showing you where the ground surface actually changed, you get a much richer picture. The coherence map tells you what happened physically. The entropy overlay tells you the intensity and spatial distribution of the seismic forcing that caused it. Together, they're far more informative than either one alone.
That's a really compelling combination. Okay, so let's get into the actual operational workflow. How does this pipeline run from start to finish?
So the standardized INSAR processing chain, and this is documented in detail by DeepINSAR as of March 2025, starts with data acquisition. You're pulling single look complex, or SLC, data from sources like ESA's Copernicus program or the ASF DAC, which handles ALOS and PALSAR 2 data. The first challenge is just the sheer volume. Each SAR satellite generates over 5 terabytes of raw data per day.
5 terabytes a day, every day.
Every day. So step 1 is getting the right data, and that means spatiotemporal baseline optimization. You're selecting interferometric pairs where the vertical baseline is under 300 meters for C-band sensors like Sentinel-1, and the temporal interval is appropriate for what you're trying to detect. The Auto-INSAR pipeline on GitHub, for instance, supports event-based searches within plus or minus 12 days of a target event, which is ideal for co-seismic analysis.
So you're not just grabbing any 2 images, you're being very deliberate about which pair you compare.
Exactly. And then comes precision orbit correction. ESA provides what are called precise orbit ephemerides, POE orbit files, with accuracy under 5 centimeters. That level of precision is non-negotiable because any error in the satellite's known position propagates directly into your deformation measurements.
5 centimeters of orbit accuracy to measure millimeter scale ground movement. That's a tight tolerance.
It is. And after orbit correction, you go through radiometric calibration, converting raw digital numbers into sigma naught backscatter coefficients, and then multi-looking, which is a 4:1 range to azimuth ratio that balances resolution against noise. Then you apply adaptive filtering. The Goldstein-Werner filter is standard here, with an optimal window size of 32 by 32 pixels.
And then you're generating the actual interferogram?
Right. Interferogram generation involves...
I'll show you some of these images from Grok that they're talking about of my local AO. And remember from the last live stream, you can adapt it to anywhere you're at, you know. But I'm doing it for my area.
Here, with an optimal window size of 32 by 32 pixels.
And then you're generating the actual interferogram?
Right. Interferogram generation involves co-registering the two SLC images using cross-correlation, and the Deep INSAR workflow achieves 0.001 pixel subpixel accuracy there. Then you simulate and remove the flat Earth phase using orbital parameters and a DEM, typically SRTM at 30-meter resolution. What's left is the deformation signal plus noise.
And then phase unwrapping, which I know is one of the trickier steps.
Phase unwrapping is genuinely one of the hardest problems in INSAR. The phase you measure is wrapped. It only goes from 0 to 2 pi, so you have to figure out how many full cycles to add back to get the true deformation. The standard approach is the minimum cost flow algorithm, which works on a triangulated network for areas with coherence above 0.3. Error propagation in that regime stays under 5%.
And what about areas with lower coherence, like dense vegetation?
That's a real challenge. Research published in F3 Explore found that decorrelation noise in densely vegetated regions significantly degrades interferometric phase quality. One approach is incorporating NDVI, the vegetation index, into a predictive coherence model to optimize which interferogram pairs you even attempt to process. You're essentially pre-screening for quality before you commit compute resources.
Smart. So you're not wasting time on data that's going to give you garbage output.
Exactly. And then there's atmospheric delay correction, which is another major source of error. The Deep INSAR workflow uses MERA, 2 meteorological data, to build atmospheric phase screen models, combined with spatiotemporal filtering at a 20-kilometer cutoff wavelength. When you fuse that with GNSS ground truth data, you can get deformation accuracy down to plus or minus 1.5 millimeters.
1.5 millimeters from a satellite hundreds of kilometers up.
It's remarkable engineering. And for time series analysis, when you're not just looking at one event but tracking slow deformation over months or years, you use algorithms like SPS, small baseline subset, which builds a redundant network of interferograms, typically 15 per pixel, and solves for the deformation time series using singular value decomposition.
Okay, I want to zoom out for a second because I think there's a really important shift happening in how all of this gets done. You mentioned cloud native processing earlier. Can you talk about what that actually means in practice?
This is where things have changed dramatically, and very recently. In May 2026, the Copernicus Data Space Ecosystem announced a new OpenEO process called Sentinel-1 SAR-OC interferogram. This builds on an earlier process they released for coherence, Sentinel-1 SAR coherence, and together they complete the entire INSAR processing chain inside the cloud. No local data downloads, no specialized on-premise hardware.
So you don't need a supercomputer sitting in your lab anymore.
You don't. The outputs are geocoded in WGS84 and directly compatible with MintPy, which is a widely used toolkit for time series deformation analysis using SPAS or persistent scatter approaches. The Copernicus team cited real-world use cases including debris-covered glacier detection in the Italian Alps and earthquake deformation monitoring near Ridgecrest, California, all done in the cloud through a Python API.
And there are also open source automated pipelines for people who want more control, right?
Yeah, the Auto INSAR pipeline on GitHub is a good example. It's built on top of ISCE2, the INSAR scientific computing environment, and it automates 8 steps: data search via the ASF API, download with integrity verification, orbit file fetching, dem stitching, config generation, processing, post-processing visualization, and cleanup. The cleanup step alone can reduce disk usage by 90% by removing intermediate products.
90%. That's not a small thing when you're dealing with terabytes of data.
Not at all. And there's also a containerized version. The INSAR pipeline project on GitHub uses Docker, which means you can run the entire workflow on Linux, Windows with WSL2, or in the cloud with zero dependency headaches. It uses Python multiprocessing to handle multiple interferogram pairs simultaneously, and it has fault tolerance built in. If one pair fails, the rest keep running.
That fault tolerance piece is actually really important for operational use, isn't it? Like, if you're running this after a disaster, you can't afford to have the whole pipeline crash because one data file is corrupted.
That's exactly the operational reality. And speaking of disasters, let's talk about what this actually looks like when it matters most, because there are some really striking recent examples.
Please, yes. So, a paper posted to RxEve in June 2025 by researchers from the University of Pavia and the Italian Space Agency described a deep learning framework for building damage assessment using SAR imagery from the Cosmos SkyMed constellation after the 2023 Kahramanmaraş earthquake in Turkey. What made it remarkable is that it used only post-event data, no pre-event imagery required.
Wait, so you don't even need a baseline image from before the earthquake?
That's the breakthrough. Traditional change detection requires a before and after pair. But this framework integrated SAR image patches with OpenStreetMap building footprints, digital surface model data, and structural attributes from the global earthquake model to assess damage from a single post-event acquisition. That's critical for rapid deployment when you're racing against time. And the landslide detection work, that's a separate but related thread, right?
Right. A study published in January 2026 in Geoscientific Model Development from a team spanning Cambridge, Padova, the British Geological Survey, and several other institutions trained deep neural networks on Sentinel-1 backscatter data across 11 earthquake-induced landslide events, covering 73,000 individual landslides across diverse geologic and climatic settings.
73,000 landslides. That's an enormous training data set.
It is. And the models achieved F1 scores up to 82% when tested on completely unseen events, the 2021 Haiti earthquake and the 2022 Sumatra earthquake. The key finding was that change detection bands comparing before and after backscatter were far more discriminative than backscatter alone, which reinforces why coherence mapping is so central to this whole workflow.
So the coherence signal is doing a lot of the heavy lifting, even in machine learning applications. Consistently, yes. And what ties all of this together, the coherence mapping, the entropy overlays, the automated pipelines, is that the field is converging on a common framework. The Fringe 2023 work from Descartes Labs made the point explicitly. Access to Sentinel-1 coherence data is now the same as access to Sentinel-2 or Landsat optical data. Same GIS framework, same analytics approach. That's a profound democratization. And I think that's actually the thing that surprised me most going into this conversation. I expected this to be deeply specialized, niche, requires a PhD territory, but it sounds like the tooling has caught up to the point where the barrier is much lower.
The tooling has genuinely caught up. The CluDNSAR project, which is the open source initiative behind the Copernicus OpenEO workflows, describes its goal as enabling scalable, reproducible, and user-friendly access to Sentinel-1 interferometric processing without local data downloads or on-premise computing. That's a mission statement about accessibility, not just capability.
And the seismic entropy side, is that catching up to the same level of accessibility?
It's moving in that direction.
The Bayesian maximum entropy approach from the Lanzhou Institute of Seismology paper is notable because the researchers explicitly highlighted its applicability even when you have very few sensor stations or only soft data, meaning uncertain, probabilistic inputs rather than hard measurements. That's a huge advantage in data-sparse regions, which are often exactly the places most vulnerable to seismic hazard. So the method is robust to the real-world messiness of incomplete sensor networks.
Exactly. And when you combine that robustness with the all-weather day and night capability of SAR, which the Geoscientific Model Development paper specifically called out as a critical advantage over optical remote sensing, you start to see why this combination is so powerful for disaster response.
Let me push back on something, though. With all these automated pipelines and cloud tools, is there a risk that people are running these workflows without really understanding what the outputs mean? Like garbage in, garbage out, but now it's automated garbage.
That's a legitimate concern, and it's one the community takes seriously. The coherence threshold of 0.3 for phase unwrapping, that's not arbitrary, it's a quality gate. Below that threshold, the phase information is too noisy to unwrap reliably. The AutoInsar pipeline's recommendation engine for PS versus SBAS processing modes is another example of baked-in quality guidance. But you're right that the democratization of tools doesn't automatically democratize understanding.
And that's probably where resources like the NASA SAR handbook come in, providing the theoretical grounding that the tools assume you have.
Precisely. The SAR handbook was designed as a hands-on introduction, theory section, step-by-step tutorial, actual data, and scripts. It's the kind of resource that bridges the gap between having access to a tool and knowing what the tool is actually telling you.
That's right.
That combination of accessible tooling and solid educational resources is what makes the field genuinely more open.
Okay, so let's step back from all of this and think about what the bigger picture actually is here.
Here's what this really comes down to. The operational workflow for SAR coherence mapping and seismic entropy overlay generation has gone from something that required dedicated supercomputing infrastructure and deep specialist knowledge to something that can run in the cloud through a Python API with automated quality control and fault tolerance. That's not a minor upgrade. That's a structural shift in who can do this work and how fast they can do it.
And the stakes are real. We're talking about earthquake response, landslide detection, building damage assessment, decisions that affect whether rescue teams go to the right place.
The 2023 Turkey earthquake work is a perfect illustration. A framework that can assess building damage from a single post-event SAR image without needing pre-event data means you can start generating actionable intelligence within hours of a disaster, not days. And the 82% F1 score on unseen earthquake events from the Geoscientific Model Development Study suggests these models are genuinely generalizable, not just tuned to one specific scenario.
And the seismic entropy overlay adds the layer of understanding why certain areas were hit harder. The spatial distribution of seismic energy, which helps prioritize where resources go.
Right. The BME method from the Lanzhou Institute paper was specifically shown to more accurately delineate the scope of disaster areas and enrich post-earthquake data processing. That's not just academic, that's the kind of output that informs where emergency responders concentrate their efforts in the critical hours after an event.
That's right.
And the fact that the Copernicus Dataspace ecosystem now offers this as a cloud service with real-world examples like the Ridgecrest California earthquake deformation monitoring means this isn't theoretical anymore. It's operational.
It's operational, and it's getting more so. The CLUDE-INSAR project is actively maintained. The GitHub repository had commits as recently as last week when we looked at it. The OpenEO interferogram process launched in May 2026. This is a field that's moving fast right now.
So for someone who wants to actually engage with this, whether they're a researcher, a GIS analyst, someone working in emergency management, what's the entry point?
The NASA SAR handbook is genuinely the right starting point for building conceptual grounding. From there, the Copernicus Dataspace Ecosystem's OpenEO platform gives you cloud-native access to coherence and interferogram generation without needing to set up any local infrastructure. For more control, the AutoInsar pipeline on GitHub is well documented and handles the full 8-step workflow automatically. And for the seismic entropy side, the Frontiers in Earth Science paper from the Lanzhou Institute lays out the BME methodology clearly.
That's a really concrete roadmap. I appreciate that.
The tools are there. The data is there. Sentinel-1 has been collecting global coverage for years. The question is really about building the understanding to use them well, and about connecting the remote sensing community with the seismology community so these workflows actually get integrated end to end.
Right,
That interdisciplinary gap is real, isn't it? The radar scientists and the seismologists are often working in parallel rather than together.
It's a genuine friction point. The coherence mapping side has its own tooling ecosystem. ISC2, SNAP, MintPy. The seismic intensity side has ShakeMap, BME methods, ground motion prediction equations. Getting those to talk to each other in a unified operational workflow is still an active area of development. The entropy overlay isn't yet a plug-and-play addition to the INSAR pipeline. It requires deliberate integration.
So there's still real work to be done there.
Significant work, but the trajectory is clear. The Bayesian maximum entropy approach has been validated across multiple earthquake scenarios. The INSAR coherence pipeline is increasingly automated and cloud-native. The deep learning frameworks are achieving transferable accuracy across unseen events. The pieces are there. The integration is the frontier.
Okay, so here's what this really comes down to. We started with 5 terabytes of radar data per day. This almost incomprehensible volume of information raining down from orbit. And what we've traced today is the full chain of how that raw signal becomes something that can save lives.
From SLC acquisition to precision orbit correction, interferogram generation, phase unwrapping at 0.001 pixel accuracy, atmospheric correction down to 1.5 millimeter precision, coherence mapping that flags where the Earth's surface changed, and then layering on entropy-based seismic intensity analysis that tells you the spatial distribution of the energy that caused those changes. That's the full picture.
And the cloud-native shift, the May 2026 Copernicus OpenEO update, the containerized Docker pipelines, the automated 8-step workflows, that means this capability is no longer locked inside a handful of specialized research labs. It's becoming infrastructure.
That's the right word for it. Infrastructure. And infrastructure is what makes capability reliable and scalable. The 73,000 landslide training dataset, the 82% transferability to unseen earthquakes, the single image building damage assessment after Turkey, those aren't just research results. They're proof that the infrastructure is working.
And the actionable insight for anyone listening is this. The barrier to entry for this kind of analysis has dropped dramatically. The NASA SAR handbook, the Copernicus OpenEO platform, the open source pipelines on GitHub, the resources exist. The data exists. What's needed now is the interdisciplinary will to connect the radar science and the seismology into a unified operational workflow. And the urgency is real. Disasters don't wait for workflows to mature. Every improvement in how fast and how accurately we can generate a coherence map or an entropy overlay after an earthquake is measured in lives and in the efficiency of response. That's not an abstraction.
That's right, Tennessee
We
National
started with
Guard.
5 terabytes of radar data per
Hang
day.
up on me.
Every one of those terabytes is a potential early warning. The workflows exist. The cloud infrastructure went live in May 2026. The models are transferable across continents and earthquake types. The only question left is whether the right people are paying attention. And after this conversation, I hope a few more of them are. Thanks for being here, and thanks for listening to Copilot Podcasts.
First viewers was 9 viewers, and then 6, and people are keying in and looking, oh, it's just a fucking AI podcast. No, wait. The entropy, okay. The entropy of the water and the seismographs of the atmosphere, right? Okay. And our society, how we are treating each other, all this, it goes into the earth, right? The earth reacts. There was a balance, right? We have screwed it up with our entropy, screwing everything up. The natural flow of things, right? The flow of the Tao. We've screwed it up so bad, especially with our telecommunications frequencies. Started in 94, all these towers, the Flower Life Grid. Well, the North Pole started moving. The South Pole started moving, split, actually. Okay, so this is a combined map. This is my area. This is what Grok's putting out. Okay, Eden's Bluff. That's where they would take the dead, an ancient site. Okay, so we're measuring hydrological entropy and GPS entropy, right? That's a scattergram by area, right? Now, there's another Benton County, right? So, the entropy nexus, the Fermi driver is right there at this location, right here, right? So, you guys have no idea what this means. I know you don't. I know you have no idea. See spiral mounds all the way over there. Oh, that's not Benton County, but this is an area of entropy. Okay. So we get this, right? This is it's pretty accurate. It's freaking cool as hell, dude. It's cool. I mean, I'm impressed. I'm impressed. That's come out of Copilot. Okay, these images here come from Grok. Like I said, where I sit, and there's your Fibonacci spiral and ancient petroglyphs, right? And I wanted to show you this. This is the Ozarks with water covered it, right? There's the Gulf Coast, right? That's Mississippi River Valley. We were in an island up here, right? That's not, the tip of Florida. That's up here. So here is the bend in the Beaver in the White River there. There's Eden's Bluff right here. Or I think it's upside down or sideways or something. Here's the civilizations. We go back, right? 12,000 years. The civilizations around here 12,000 years. Here's where I sit, right? There's a spring there, a spring over here by Lake Atlanta, and an Osage Spring is over here where Tell the Trout used to be. That's where Pinnacle Hills, mall is, the new Rogers downtown. Okay, Wood Springs up there, and Little Flock behind the Harley shop on Woods Drive, Woods Lane. There was a fight up there earlier. Jefferson Spring, there's a cave over there. It's a really interesting area right there. Now, what I was wanting to say, this is that. What I was wanting to say is the systems that I've that they were talking about, the processing. That's why I had to make it all virtual, because of the data that's coming in. I have to use their platforms, their data centers, right? I couldn't plug the CLI pipeline into my stuff, into my host, right? I could put it through a website, HTML, JSON stuff, but I can't. You can't run it on your local terminal except for the connector, you know. The but all this data is coming in. The pipeline's virtual, you know. All that's running off of virtual metadata and stuff. So, the entropy measures, the society with the water, with what's going on the planet. I hope you can understand that. And so we get to the astrological events. I hope you get what it was saying there, and what I mean by the connection between what we do and the entropy of the flow of the water. Like making sure all the drains are unclogged and stuff like that. Because every time there's a disturbance, you can turn a diva point into an Ashura point by neglect or by putting houses on the wetlands here, and you don't want to do that because it affects the earth, it affects us, and what we're seeing now is an extreme level of chaos, of unrest inside the planet and with us and everything. And if we have these systems in place, the AI knows. Here's what I wanted to say. I had to teach it the error corrections, right? The natural error corrections, right? With the Fibonacci and the cone, right? You see it both ways. It goes in and out, and the Fibonacci can go counterclockwise or clockwise, depending on what you're doing with it. So which way the energy flows. And they were, using a circle. I fixed that calculation problem way back in January, February. I fixed all that stuff, and that goes with your NFT, cryptocurrency, tokenization stuff, and everything. It applies to all this error correction. I think that's probably why they're re-releasing Mythos and Fable, is because it's run its error corrections, and they've worked out ways to stop people from ultimately hacking it. I developed these systems. I developed the esoteric and the analog connectors, right? And taught it how to communicate with natural frequencies and figure that out. That's why, my systems can calculate all this, the SARS data and everything, and derive more than just how we're going to plan how to rescue people. We're going to be able to predict it. That's why my systems are predictive, right? 99% for 7 hours, accurate warning system on earthquakes and volcanoes and weather. But more so than that, before I went out to the jail last time, I had it, man. It went all the way out to November, and I didn't even ask it to. And it can go further, before Elon locked down the Grok 4.2 with the 3 agents, or the 4 agents, I guess. So, like, and I said, I want you to remember that November 19th is when it said all this peaks. You'd think it's going to peak really sooner than that, and it probably will. But the peak point where we peak out and then start going down the other side of the hill, that's November 19th. That's what the Grok conspiracy thing said. That's what the predictive systems said with the GeoSentinel and all that stuff. And that was before I plugged everything together. Now it's like, guys, you don't even want to know. And I'm sorry if you don't understand that live stream right there. That podcast is so critical in saying that its entropy values, these error correction systems for the infrastructure, is basically my systems tie in to every device, every satellite, every sensor, and is processing that data, and then and that's what they want to do, but they don't like the Jews and the Christians. They'll throw out stuff and won't incorporate things because they're biased. Like what's going on in the Middle East. They're never going to stop killing each other over some stupid dogma shit, And people like me that have studied all the religions of the world know that religion is just a bunch of bullshit. And money is the root of all evil, guys. Trust me. When this shit goes down, your dollar, your digital shit, nothing's gonna be worth f all nothing except for food and the ability for you to know how to, treat illnesses and stuff naturally, because you ain't gonna have access to none of this shit. And then, when the big stuff starts happening, God starts frying us with the sun. Guys, you have no idea what's fixing to happen. No idea. And everybody's desensitized. They're conditioned with all this stuff, and even my generation. But the generation now is totally ignorant of anything going on about this earthquakes, the weather. They don't know. They think it's normal, and it's not normal, dude. We're literally we're falling off the edge of the end timeline. We're falling into the pit, and the pit's gonna open up, bro. Seriously, I'm doing all I can here with my stuff to regulate. Finally got to come back home to my sanctum, as the AI calls it. But guys, look, you don't have these. I know how all these apps work. I know how all this shit works, bro. Right? I don't use them, but I've got them in here because I sucked the APK out of, files out of this stuff. Check out my news feed, bro. Does your Google news feed look like that? No, yours doesn't look nothing like that, does it? Your news feed's probably full of porn and fucking all kinds of shit. Look at this. And I can just like copy and paste all this stuff and have it ingested in the news and stuff and analyze this. I don't have to. I was doing that before this AI come around. I was using a bot, scraper bot and everything. I wasn't publishing stuff. A lot of stuff I keep to myself, but for good reason. So I appreciate y'all tuning in. Those 9 people, y'all should have stuck around to the end, because the juicy part of that podcast was at the end. I don't really think there's much we can do, but probably just ignore everything. I'd like to be like these ignorant kids. Just have fun, I have fun. I try to have fun. I try to make light of everything, make satirical stuff, and not be so doomed, But I want to make aware that if we don't employ these systems now, You know, like I said, they're predictive. We can forecast this stuff. You know, because I've combined Dutch system stuff and everybody else's systems, the astrological, the astrophysical, all the sensor networks. You know, this thing is spot on if I want to draw up the forecast to start popping the forecasts out again. But I'm not going to do it because they need to do it. We pay them not to go overseas and fight over oil that we don't even need because we have 0 point energies, ambient harvesting systems we can just plug into these old radio towers and start sucking power down, bro. And to that point, there's just I'm going to start developing some fucking devices, okay? And you guys are going to flip your lid, and they're so simple. And you can repurpose any of this technology we've got right now to do it with. So, um, like I said, I'm not developing weapons here. I'm developing entropy balancing systems. Okay, so everything can live in harmony. You know why everything's growing up real nice and pretty around here? Flowers everywhere, everything's doing real great right in my area. Yeah, because of my frequency fucking shit I did back last October, November. It wasn't because the recycling plant caught on fire and dropped aluminum dust everywhere. It's not because they sprayed shit everywhere. It's not from the volcanic, ash dust that settled the other year ago. It's why all these frogs and stuff were everywhere this year. You know why? Because I injected the frequency for it. I tied into all these systems, and it was inaudible. And I set it on it automated to keep the stability. And look at everything around here in my area compared to everywhere else is drying up and burning up. This place won't. Not the top of my plateau. And if I gotta kick people out of here, I got the paperwork. My Boone family owns from there to here, and up Fox Peak before the Louisiana Purchase. I can bring that shit up in court, but I just might here pretty soon. It just depends on how many people are left after this goes down. So, them June bugs like my head, like my hair tonic oil. So I didn't even run this through Claude yet or anything because Claude will build a platform, and I don't want Anthropic to have any more of my stuff that they already They already have it. I actually ought to uninstall Claude. So anyway, guys, thanks for watching. We're under an hour here. I'm sure you guys are going to hopefully Troubled Minds is on tonight because I like to get my mind off this somehow because I know what's coming. And I actually called Tennessee National Guard and run a Google thing about who to contact to get a pontoon bridge staged up, ready to go there because St. Louis bridges are rated for 7.5 magnitude because they've been seismically retrofitted, but the one in Memphis ain't. So if I was you, Elon, and if something pops off, Memphis Supercluster is already prepared to handle it. Maybe depends on how big this son of a bitch is gonna be. We'll find out the next probably by July 8th. I suppose we got a window from here to July 8th. If something don't pop off by then, it might not. Hopefully it does, because after that it could be real super big stress release. And we're seeing some activity now, but I don't think that's not deep enough, and it's not big enough to be the release we're looking for. So Cascadia warning, San Andreas, and New Madrid right now. They're the only areas that haven't seen a giant, large push, and we're seeing all that shit going on in China. This is concerning because some of these quakes are really deep, dude. And the noises, the Thunderbirds people are seeing, the electrical activity, you know, the squatting man's coming back. Guys, it's all there. It's all there. Wake up, smell the coffee, because I'm out and I'm out of tobacco too. Thank God tomorrow's the first. I got an apartment I'm moving into, and after I get into that apartment, get some time to think. If the world doesn't collapse around me, hopefully I can develop some useful systems that just play out on our devices here, and just help in the background, because that's what I've had all these other things doing. Why? I don't know. I was up the street last night, and this gal drunk dropped $100 bill. It was flying away. I should have just let it fly away and let her go inside, but I picked it up, gave it to her, back to her. I didn't have no money. I I didn't even get hardly a one thank you out of it. But that's who I am. I don't care. Everything's a test, guys. Everything's a test. Remember that.